So now we will look into first vision language pre-training model. So now so we have already covered this basic form of combination of this vision encoder. So now let's look into pre-training of large vision language models and this so-called foundation model. And we will particularly look at autoregressive way first, and one of the early works in this autoregressive is Uniter. So we will look into Uniter first. So this kind of vision language autoregressive pre-training will enable us to do a lot of stuff. For example, we can do captioning, describe a scene, describe a video, and so on and so forth. We can look into visual question answering. We can do, so you can do dialogue, you can do text to image retrieval, image to text retrieval, image to video retrieval, text to video retrieval, video to text retrieval, and so on and so forth. So you can do a lot of stuff with this kind of transformer or multimodal interaction. So let's look into Uniter, which is one of the earlier work. So it's published in ECCV 2020. So there is a lot of things going on in this picture. It's quite busy, so I will try to break it down. So before we start to jump into this vision language model pre-training, so let's look into that how they are trained overall. Let's step back and see how they are trained. So what you need is a data first, yeah. So to train these kind of model, you need paired data. So you need to have images and you need to have corresponding description of those images. Yeah? And we have a lot of data set which do have this kind of capability. So for example, we have MS Coco, we have Flickr. So Flickr has 30K images which are paired, vision and language pair. MS Coco has around 80K images, so they have around 80K images which are vision and language pair. So there are multiple annotation corresponding to each image provided by the human annotator. MS Coco also have multiple. I think MS Coco may have 10 human description provided per image, and Flickr has around 5, I think. So, but I may not remember them correctly. You can look them up. So these are fairly small scale data set. There is visual genome as well. So visual genome has around 100,000 images. But the good thing is that visual genome has bounding boxes and the description corresponding to those bounding boxes as well. So it is quite detailed, yeah, and it is much more complicated image than MS Coco and Flickr. So we have also conceptual caption. So it's a data set which is a link of the images and corresponding text associated with them on internet. It's around 4 million when it was released. If you download it in 2 days, probably it's going to be around 2 million because many of the links are not available anymore. So this data set is weakly coupled data set. So what do I mean by that? So people went on internet, they look at the image at a website and the text associated with that image on that website. Yeah, so people do put image and they do put text associated with it. So this is the combination of those. So sometimes that text is going to describe that image, and a lot of times that text is not going to describe that image. Yeah? So it is having a lot of noise as well, and that is okay. So these kind of vision language model are able to handle these kind of noise, particularly if that noise is present in the pre-training set. So that is something which you use to pre-train vision language model, all of them which are coming through. Yeah. So this is kind of the data set which you use. You have bigger data set as well. For example, you have line data set as well. So that is having different flavor. I think one is 400 million, and they have 3 billion, and they have 5 billion as well. So if you do have compute and resources, you can train on some serious data as well. And then in-house data from tech giants is even bigger. Okay. So this information flow is a little bit weird here. So what I want to show you is that there is this man and a dog sitting on a couch. So that's the image, yeah. So just for the reference. So essentially, I took the image from the paper directly. So this thing should go on the top, yeah. But that's fine, yeah. As long as you understand, that is okay. So we give text at the input because I told you that image and text are given together to these models, yeah. So you need to have coupled the image and corresponding text associated with that image to train these models. So you use the text and you do the tokenization of the text. You have done the tokenization of the text in the lab and many other places you would have seen when we were discussing. So you do just simple tokenization. Yeah. For image, it is the work coming from 2020. So at that time, an images were 16 by 16 paper was not out, yeah, because that came in 2021, end of 2020, 2021. So they have no idea, no way to patchify the image and pass it through the transformer. So what they were doing is that they were using object detectors. You apply some state-of-the-art object detector and you detect objects or regions of the image, and you pass these regions to the transformer input as well. So what does an object detector gives you? An object detector gives you the representation of the region, which it is saying, representation of the bounding box, and that representation could be in different dimensions, so it can be 1024 or the more dimensional vector. So that's first thing it does give you. It gives you the label. It's actually gives you the probability distribution over the whole set of classes you have. If you are trying to detect 2,000 classes, so the object detector will give you the distribution of all the classes, that what it think is this object, what it think the object is in the bounding box. So it gives you distribution of that, and if you pick the maximum, response, that will give you the bounding box. Yeah, so that will give you the class. Pick up the maximum probability corresponding to the maximum class, that will give you. So it gives you the label, it gives you the distribution, it gives you the feature map. The feature map is before the classifier layer, essentially. Yeah. So these are the three things which it gives you. So what you do is that you typically, when you take VIT base, so your text encoders are typically the text embedding space typically consists of 768 dimension. The typical the region extractor or object detectors give you 1024, 512, or 2048. So you need to have a linear layer to convert from the dimension from 1024 into 768 or something. So once you have the same dimension, you pass it through a transformer. So remember, so this is the case where you have a shallow vision encoder. There is a heavy duty network which went before this for the vision, because you have the whole object detector. Yeah, so you have 152 layers or something. So they are using some variant of CNN model with hundreds of layers. Yeah, so you have a large CNN model which is giving you the regions and objects and labels and so on and so forth. So you have that, and then you have a deep transformer block, which is this transformer consisting of 12 layers or something. Yeah, so you have multiple layers of them. And what you do is that you have this multi-model unified transformer which will do the QKV from both the images as well as text. Yeah, so it will just consider that as a data token, and you will just pass those data token through this transformer. Of course, you will add modality specific embedding. You will add position embedding for the modality. You will add modality specific embedding as well. So for example, you will tell that this is vision, this is text, and you will put the special token which is start and end of the image and so on and so forth. So all of that is there. Yeah, but in principle, you will consider these multiple tokens and you will pass all of them to the same transformer, and you do good old self-retention and feed-forward network and multiple of them. That's it. Now, when it comes to how you train this, then it becomes very interesting. So one of the way to train this is that you do mask language modeling. So you take only the language part and you mask 15% of them randomly. Yeah, same as what you have done in BERT. Yeah, so we have studied this loss in BERT as well. So you take 15% of your text token and you mask them, or you replace them with noisy words or so on and so forth. The same strategy as in BERT, and you use both visual token as well as text token, the rest of the unmasked token, to recover it. Yeah, so we have seen that in detail before. Okay, so that is called masked language modeling. Yeah, that is the last at the bottom right. Okay, bottom left. Then you do masked region modeling. So that's another loss which you do. So here the object detector is giving you regions, and you basically go and mask those regions and you recover that. With respect to text, when it comes to text, you have the dictionary index of that text label, yeah, and that's your class, and you can recover that very easily using negative log likelihood. Yeah, so you will use negative log likelihood for this loss. When it comes to region masking, mask region modeling, then you have multiple choices. because the regions has the feature vectors, 1024 dimensional or 2048 dimensional feature vector which was given to you, and it does have the label as well. Yeah, so you can choose to recover the label in the same way as you are doing for the language. So that's one option. The second option is that you can choose to recover the feature map, yeah, using L2 distance. As you have seen, for example, in SIT, you are recovering the pixel space using L2 loss or L1 loss. You can choose to recover in the feature space. We have seen also some of the networks which were doing recovery in the feature space as well when we were doing the cell supervised learning. So that's another option. We do have the probability distribution over the whole set of classes. So you can choose to do that probability distribution and you can recover that. And let's look into mathematics of this. Yeah. So you have masked language modeling. So this is very simple. So you want to predict the missing token. So this is the probability of the masked token. So probability of the masked token. So this is a word which is masked, given the unmasked word and all the visible regions. So you want to recover the masked token, and you want to recover the masked token. This is the loss, yeah. So this is the probability of that masked token. You take the log, negative log of it, and you sum over the whole batch, and that's give you the loss, yeah. So it is very simple. So you are given the unmasked token, visible token. So this dash slash m mean visible token, unmasked token. These are vision token, the region token, and your task is to give your network needs to give you the probability of masked words which you have masked. Simple, yeah, using negative log likelihood. So this is negative log likelihood function. So we have studied this in detail. Okay, and we have seen the region tokens as well. So for the case of region token, so you will use some f. Now this f has 3 flavors, and we already discussed these 3 flavors. If you are recovering the label, the ground truth label for that region, which is provided by the bounding box extractor, the detector network. So you consider the output of detector network as label, and you will use that, and you apply the cross entropy loss to recover. Okay, so that's one way. You can use the feature map, which is given by the region detector network as the feature for which is representing that region, and you can choose to do L2 difference on that. Yeah. So, or you can do the distribution which the network is giving you, and then you can do KL divergence, essentially cross entropy as well. Okay. So that's what is going on with this mass region modeling. Very simple. Yeah. So then you have 2 other laws. One is image text matching, and the other is word region alignment. So let's look into that. So let's look into image text matching. So image text matching is very simple. We have studied this this net sentence prediction laws in BERT as well. Yeah. So when we had language, so if the 2 sentences are same, then the label is positive. If you randomly pick any other sentence from the data set and couple that to the current next to the current sentence, that will most likely will not make sense, yeah, because those 2 will not convey the same thing, so that will be negative. In the same way, if the image which you are giving, regions from the image which you are giving, and the text associated is from the same paired data, then that's a positive label. And if the text is provided corresponding to a different image, and then it's a negative pair. Yeah. So it's basically binary cross entropy loss based on positive and negative. And how you extract the positive and negative? You have a batch, and you have the same paired data from same image and corresponding text. That's a positive label. Take any other text from the batch, that will be negative label. Yeah. So and then you go and do good old binary cross entropy. Yeah. So that is image text matching. So this is the definition of binary cross entropy. We covered that in detail before. Okay. The last 4th loss is word region alignment. I will not go into detail of that. Yeah. Because it involves quite heavy duty mathematics. So it is something they are using something which is called optimal transport or versus time distance. So basically you use this to measure how much effort you need to move one set of mass to another. So how much effort you would need to go from one probability distribution to another probability distribution. I will give you a little bit of overview, but I will not go into details of that. Okay, so there are words and there are visual regions. Yeah, so there are these are the words which are given to you: man with dog on a couch, and there are corresponding regions, not corresponding region. There are regions which are the region detectors is giving you, which the object detector is giving you. So these words are represented by WI, and the visual regions are represented by VJ, and CIJ is giving you the cost between word and region, and that cost could be as simple as your cosine similarity. Yeah, so you can just take the word region representation, word representation and region representation, and you can do just the dot product, and that gives you the cost. Yeah. Then you use some iterative algorithm to estimate the weight corresponding to the cost, and that the T, the transportation matrix, it's called transportation matrix. You need to learn that, and to learn that you use some algorithm which is called IPOT and things like that, and it's quite mathematically involved. You can look into some of the publications which we have, and you will see the maths and details of that, but it will take probably more than a lecture full to just go into mathematics of that. So, but you understand the concept. You have the cost, and you need to find the weight corresponding to those costs, and that will tell you that which word is aligned to which text word is aligned to which visual region, essentially. Yeah? So that's word region alignment loss. So we are not going into detail of that, but the citations are there. You can take a look at there, or you can go to our Google Scholar profiles, and you can take a look at there as well.